again, an analog. It's not exactly the variance, but it sort of gets you at the covariance matrix really quickly. But I'm going to show you some other things real quick here. Okay, how are we doing? Questions? No. Why does it matter? Here, let's do a couple more. The identity matrix, as I mentioned before, it's kind of like the number 1. To make an identity matrix, it has, remember, the size of the identity, to do the multiplication, A times I, the number of rows of I has to match the number of columns of A. But if you form that identity matrix, which is actually going to be diagonal with 1s down the diagonal and 0s in the off diagonal, then you will receive A back. Right? Similarly with I times A, the pre-multiplying version of that. Now again, the columns of I have to match the rows of A. So let's see here. No, that's this one. Here we go. Let's go back. Go over to the R section here. So here, X transpose X, you saw us form. We could also, in R, there's a function called diag, which does that. But let's imagine here's X transpose X. X transpose X had 2 rows and 2 columns. So if we wanted to show what happens with the diagonal matrix, oops, I could do diag, and I'd need a 2 by 2 matrix to multiply it with, right? So sure enough, look at that. X transpose X times this diag 2, right? This is diag 2, gives us just X transpose X back. Now, why is that the case? Let's talk about that for a moment here. Go back to my slides. If we were to, let me just do some erasing here. Get out of here. There we go. Sorry, my sound effects are heavily Huey influenced. He likes it when I make sounds. And of course, as a dad, I pay attention to that. Oh, yeah, he laughs. That must be funny. If we multiply this first matrix right here by this second matrix right here, what happens? How do we form it? Remember how the matrix multiples work? The first element of that comes from this dot product, effectively, of the first row times the first column. And we have SAT variables squared times 1 plus this cross product times 0. We sum those together, and we're left with the sum of SAT variable squared up there, right? And the same thing happens as we go along. What is the second element up here? It's this row times the second column, which is 0 times SAT variable squared, but a 1 times the cross product. I'll just put V and M up here. Similarly, if we want to go to the bottom element, element 2, 1, that would be row 2 times column 1, which is the sum of the cross product again, VM, because 0 multiplies SAT math squared. And the last element, row 2, column 2, comes from column 2 multiplying row 2, row 2 multiplying column 2, which is 0 times the cross product plus 1 times SAT math squared. So that's the sum of math squared. Yeah, Alan. That's right. Yeah, so the identity is just this diagonal of 1s. Sometimes you see identities in multivariate, in our multivariate regression when we get to, because one of the first things that we talk about is we have to figure out what we're going to do with variances for each of the variables in our analysis. And one of the quick ways people model that is to take a scalar called sigma squared and multiply that by an identity. Imagine we have 3 dependent variables in our analysis. Remember what happens when we multiply a vector by a scalar or a matrix by a scalar? It's that scalar times each of the values in the matrix. So this would lead us to a matrix with sigma squared down the diagonal and zeros in the off diagonal. Or basically, this is the assumption of homoscedasticity. So when you see identity in statistics, particularly when we get into things, it's often talking about a very simple, naive way of thinking about variance, that every variable has the same variance as you go along, right? Because you can quickly say, I've got sigma squared and I've got this matrix. Weird. Other questions? Okay. Next, zero vector, as you might imagine. Vector of zeros. Not really much interesting there. If you want to, if you multiply any matrix by this vector, it gives you a 0 vector back. But again, the number of rows of the vector has to match up with the number of columns of the matrix to be post-multiple, right? Or the number of columns of the vector has to match up with the number of rows to be a pre-multiple. Vector of zeros. Finally, the ones vector. One of my favorite terms. Vector of ones. Really, not that interesting, right? No. But it's very useful because, watch what happens. If we have, let's take a little vector x, right? And let's imagine this is the vector of values 1, 2, 3. Fair enough? Right? What would x transpose 1 give us? So again, x transpose now is this is a 3 by 1 column vector. You can think of it as 3 observations. So if we take the transpose of it, it would be a 1 by 3 matrix, a row vector. So we need to multiply that by a 3 by 1 to make the multiplication work, right? 3 by something. So this is a column vector of 1s. So we know the resulting matrix will be size 1 by 1. But how do we get the numbers? It is the first element times the first element, or 1 times a 1. Second element times the second element. 2. Third element times the third element. 3, which equals 6. It's the sum. So quickly, if you wanted to find the sum of a variable x, it's actually equal to that variable x transpose times 1. You can quickly build sums in matrices with the ones vector. Because matrix algebra involves multiplying and then summing things together. So if you code in 1s in the thing you're multiplying, the sum is 1 times all the numbers in your matrix. The other thing I'll note to you is that this column vector of 1s shows up in every one of our regression and ANOVA models where we have an intercept. It is the corresponding column of data that goes into the model to make an intercept show up in our output. It's literally a column vector of 1s going into that X matrix for our data. So, all right, how are we doing? Yes, Ahmed.
So if we have missing data, if we would like to run the correlation between two variables, we have to print the missing data. So we wouldn't have NA in that cell.
Right. Yeah, that's the problem. There's no matrix algebra for missing data aren't numeric. Right? The NA code can't do math with. So the options for doing missing data start to get limited. One idea is in R, there's a command called na.rm, which pairwise removes each observation. Actually, in covariance matrices, there's several options. There's a listwise, which deletes if one observation for a person is missing, then the whole person's omitted. There's pairwise, which means if one observation of a pair of variables is omitted, that pair is omitted. But generally speaking, neither of those are good options for what we do because oftentimes that missing data can bias our result if we're not careful.
So what's your quick advice for dealing with missing data?
Start doing qualitative data analysis. Just kidding. There is no... the other option is be clairvoyant. I think it depends. There's varying levels of complexity with what you can do. And I don't remember if we have missing data on the lecture list anymore or not. I think it's still there. When we get there, we'll have a whole lecture on it where we talk about there's certain layers of missing. But one of the more standard layers is something called missing at random, meaning that the missing data is somehow related to the other data that you collected. And so in that case, if you use an estimator like maximum likelihood or like Bayesian, something has a likelihood function, that for the observations that are missing, it just doesn't get put into the likelihood function, then the estimates from that are somewhat resistant to missing data when they're missing at random. So for instance, I know you took my SEM class, you're familiar with Lavon, M plus does the same thing. The saturated model in a model that we're going to talk about here in a few days, when I talk to myself on the computer, you'll hear about this soon. It shows up in every structural equation model. It has the full covariance matrix estimated, but it's estimated with that maximum likelihood in Lavon. So that thing that it estimates is actually probably the best estimate of that correlation or covariance matrix that you can do quickly. But other than that, the options are bad or potentially bad. It depends on why it's missing. So good luck, right? All right, other questions? Okay, how about division? Again, it's still sort of making me roll over, like get sick inside. It's not exactly division I'm talking about, but hear me out. Remember division back in algebra? If you took A divided by B, you could really reformulate that as 1 over B times A, right? Or you could really reformulate it as B to the negative 1 power times A. Remember that? Okay, well, let's just pretend that you remember that. The second thing I want you to remember is that a number divided by itself gives us a value of 1. Right? So those two things are sort of the features of why I'm calling this matrix division. Because we'd like the same properties to show up in matrices as well. A matrix inverse is indicated by a matrix raised to a negative 1 power. And for this, we're going to stay with square symmetric matrices because it helps the math stay good. And most of the time we want a matrix inverse in what we're doing in statistics. It will be an inverse that is a square or a square and symmetric matrix. Remember, square is symmetric. It's a square. The numbers that are above the diagonal in the triangle are reflected by the numbers below the diagonal in the triangle, right? So when you form the matrix inverse, it has the properties such that A inverse times A as a pre-multiplier gives us the identity matrix back. Right? That's that property I'm telling you about of a matrix or a number divided by itself should give us 1. If you're thinking that the identity matrix is like the analog to the number 1 in scalars, then the inverse matrix kind of functions like matrix division. A inverse times A gives us the identity. And actually it works in the same in reverse as well. So long as we have square symmetric matrices, the sizes, the dimensions make it work so that this multiplication here works. Like 3 by 3, the inverse of it's 3 by 3. Any square symmetric matrix can be a pre and a post multiple just fine because the rows and columns are equal to each other, right? With me? Maybe. Bored, but with me? Just taking my word for it, one of those. That's an inverse, so we could do the same here. Now, I will note the calculation of the matrix inverse is pretty complicated. I remember when I took matrix algebra, I actually took a whole year of it, spanning undergrad and grad school. There was a big section of that course, at least the first one as an undergraduate, where we computed these by hand. And I remember it was in a statistics class in graduate school, a graduate statistics class on linear models, and the professor made us invert a 4x4 matrix by hand as part of a timed final. And we couldn't use calculators. Like it was ridiculous, right? Anyway, actually, yeah, it was pretty ridiculous. Thankfully for us, we don't need to worry about that. We're just going to let the computer do the inverse. We're fine. The other thing about inverses is that they are notorious. There's a lot of computations involved, and there's better ways of doing them than others. So not all people who are using matrix inverses are good. This is where you can have something called an issue with numerical stability. I don't know if you've ever heard this before. But if you're not concerned about the number of rounding, the amount of rounding that's going on, I'm trying to make this a pretty direct way of saying it. If you're not worried about the amount of rounding of digits in what you're doing, when you take lots of calculations that are dependent on yourself, that rounding error can propagate to give you results that are what we call unstable. Right? The numerical instability is what we call it. So there are a whole set of matrix algebra packages that our government, the U.S. government, paid for during, I believe it was like the 1960s and 1970s, basically when we were trying to put people on the moon, to make sure that there wasn't some rounding error miscalculation that would sort of miss the moon. That would be pretty bad. I know you laugh about that, but you think about like the number of times, you all have your computers up here and you're bored by this. Google how many times people have failed to reach Mars or failed to reach like the moon. And I think it's not all matrix numerical instability that's causing that, right? That's a lot of stuff. But there's, anyway, pretty well-known ways of doing it. We just never teach it in statistics. So that's one of the dangers that show up. The other thing I'll note is that not all matrices can be inverted, right? Matrices that cannot be converted are sometimes actually called singular matrices. Seems really weird. If the matrix does not have an inverse, it's said to be singular. And when we see these singular matrices, it's oftentimes because of linear dependencies. Like if we have multicollinearity, extreme form of it, of real linear dependence in our data, that would be part of that. So, moving forward, here's an example of the matrix inverse. I'll just flip over to R for it. You saw our X transpose X inverse, actually. We have X transpose X here. We can actually, the function in R that does the basic matrix inverse is called solve. There's a number of ways of doing a matrix inverse, but this is one of the most direct ways. So if I form this matrix inverse, you can see all these very, very small numbers, right? Really tiny. So now I'm going to take X transpose X inverse and multiply it by X transpose X, the original matrix, and it should give me the identity. But it actually gives me, see the ones down the diagonal, and it gives me very small numbers in the off diagonal. Those numbers are effectively 0, but that numbers are part of where you start to see the rounding error that shows up with this. Right? It's a really computationally, I mean, for a 2x2 matrix, it's not that complex. But as the matrix size grows, it's much more complex. And so you can see there's an amount of rounding error in each one of these calculations that we're doing. Similarly, we could take X transpose X and multiply it by X transpose X inverse, and we'll see the same thing. How we doing? Bored. Do we have to? All right, here's some operations. Guess what? Read those yourself. No, sorry. Try to make it less boring. We're going to end our discussion about matrices with some advanced topics. All of these are related to statistical analysis. Let's imagine here we have a correlation matrix of our SAT data. We saw this before. You can actually compute it yourself if you want. We have ones down the diagonal, and 0.78 is the correlation. So that's a correlation matrix. It's square. It's symmetric. How many rows? How many columns? All right, you passed. There's something called the trace of a matrix. The trace of the matrix is literally the sum of the diagonal elements for a square matrix. So the trace of a correlation matrix is 2 in this case, and in general, equal to the number of variables you have in your analysis. Yes, that's right. Left to right diagonal. Very good point.
Left to right diagonal,
Downwards, that's right. Left to right. Starting in the upper left-hand corner in position 1, 1, and ending up in the position that's the last row in column itself, yes. So yes, so this is something to consider. In a lot of statistics, particularly in exploratory factor analysis, have any of you had exploratory factor analysis in your career? A couple of you, not a whole lot. We talk about proportion of variance explained. That proportion, the denominator in that comes from the trace itself. Right. So the sum of the variance or covariance matrix. Covariance or correlation matrix, excuse me. There's another part in matrices that we need to talk about, and that's the determinant. The determinant of a matrix looks like the absolute value right here. It's usually just a single bar around the matrix. It is a scalar. It's a numeric value that characterizes something about the matrix itself. Now again, for a square matrix, the determinant helps us indicate whether or not we can form an inverse. If the determinant is positive, the matrix has an inverse. If the determinant is negative, the matrix does not have an inverse. There's some type of linear dependency. And at 0, it's sort of an interesting case. But technically speaking, our determinant for our correlation matrix is 0.3916. If you have a larger matrix than 2 by 2, it's really tedious calculation also. So the determinant shows up. It also shows up in statistics in that we're going to call this a generalized variance of multiple variables. What? So we know what a variance is, right? If you collect 2 variables, each of them has a variance. It's a measure of spread for each variable by itself. But what about the measure of spread for both variables together? That's a little weird. Think of it this way. You've got those vectors that are going off into space. How much of what size is there of that geometric thing that you have where the vectors are enclosed in? That's what the matrix is telling you. It's actually giving you the volume of that whatever dimensional space, sometimes called a hypercube or hypersphere or whatever else, with the variables in it. So it's a one-number summary of how much variation there is in all of your data. It's an odd thing. So also, just a couple other notes. A positive determinant means a matrix is positive definite. A determinant that's not positive is non-positive definite. And I guess there's one more. A determinant at 0 is sometimes called positive semi-definite. It's trivia at this point. We may hear non-positive definite matrices. Yes? That means it's trying to form an inverse, and it can't, usually. Where you might see that, also the times that you might see that would be in, has anyone ever used SAS to do linear models before? No, never mind. Yeah, if you get, do you remember which package or which stat you were using? No? Yeah, that's exactly it. Usually means there's a linear dependency in something it's trying to do. Depending on the method you were using, that could mean a lot of different things, though. For linear models, it usually means something's going on with the X matrix. There's some multicollinearity going on, because that's usually which indicates the problem. It could also, I'll just leave it there. There's other ways it can happen. All right, how we doing? Okay, we have 20 minutes left. I'm not letting you out early yet, because this semester has been sort of a interesting one for me. My son had the flu last week, by the way. Fun times. Yeah. Like if you were to take a number and put 1 over that number, like the inverse of 4 might be 1 over 4 or 0.25, and that's because 4 times 0.25 gives us a 1. So it's whatever might take an original matrix and make it the identity. That helps. All right. I want to pull up the other set of slides I had for today, if I can. Questions while I'm doing this?
Do you always use the correlation matrix with the determinant?
Not always. It's actually more frequently in statistics. We're doing the we're going to be doing the covariance matrix, where you most often see it. Oh my goodness, it keeps giving me the same folder, and it's not the one I want. Watch this, desktop. It's Groundhog's Day, desktop. The biggest problem I have with the Mac is the Apple products I have to use with it. Let's try this again. Drive. There we go. I have a crazy filing system. Teaching, actually, hang on. What PowerPoint? Anyway, the next lecture is about matrix algebra and about multivariate normal. So it starts to put some more context, I hope, to this discussion. Online, which is not online. There you go. You can see my filing system. It'll break. No, it's downloading. That's good. All right. Broke earlier today. Working on it. So now this is an introduction to multivariate normal. If I don't get through all this today, I'll put this up on the videos on the lecture. I want this to be here because it provides hopefully a little bit more relevance to what we're talking about in matrices. So here we go. Yeah. Yes, it should be. Yes, it should be. Same as the website, yes. Unless I screwed that up too. Oh, come on, man. I don't even know where that goes. There it goes. Okay, I can move this around. All right. Okay. So we're going to play with matrices and data. Here's our data again. Let's talk about statistics and distributions. Up to this point, we have focused on the prediction or the modeling for a single dependent variable, single outcome. And in what we knew before, this was something called a conditional distribution. Right? Conditional normality. This is a linear or generalized linear model. But multivariate statistics is about joint distributions. So that means multiple variables that are outcomes simultaneously. So therefore, we have to do a little bit of adaptation for what we do, like a joint distribution, but we get different things. So here's some numbers. Let's have some fun with some data here. If I go grab the other R section here. This is the R syntax from online as well. One thing I can do is I can show you some of the features of matrices that make them cool for statistics. Number one, if you wanted to form the mean for a bunch of variables all at once, when you have one variable, it's just the mean. When you have a bunch of variables, like in a multivariate data set, it's now going to be called the mean vector, a vector of means. Sound good? It's a mean vector. All right. X bar, it's in boldface, so it's a vector, comes from 1 over n times the product x transpose times the 1's vector. And what it results in is a column vector of each of the means of all the variables. So, going to data, right here, what I can show you is, here's the number of observations we have, actually 1 over n. Here is the 1's vector, it's a 1,000 by 1 vector. We saw before x was 1,000 by 2, so that means the transpose of x is 2 by 1,000. So 2 by 1,000 times 1,000 by 1 is multipliable, because the columns of the first match up with the rows of the second. And sure enough, when we do all that, we can see the mean vector is 499.32, which is our verbal mean, 499.27, which is our math mean. Just like that. Or you could just use the mean function. But in the packages that you're working with, in this case, there's a package called MVT norm. If we were to go and type, if we wanted to take, remember how we found the height of the normal distribution before? In the multivariate normal, we have to do the same thing, but now we have multiple variables that go into it. And if I showed you the function for it, they're actually doing that with matrices. I won't show it to you. Never mind. Too much information. Next. What does the mean vector do graphically? Here's a scatter plot. This is the row vectors all plotted together, or the variable SAT math and SAT verbal. Look at that. That mean vector is right in the center of that sphere of data, or that mass of data. It is the, what am I looking for here? Kind of the balance point. If you're trying to talk about that, if this were actual mass, it'd be the fulcrum, the balance point of the mass itself. You could balance it on the point where the mean happens to be. Cool? You can give me like a one. Maybe we should have a rating system. Cool is like a 5. When I say cool, I'm like, yeah, that's awesome. 5. Or like 1 is like, no, not cool. And it's okay. Like, anybody want to like raise their hand? So if I say, is that cool that the mean is kind of like the balance point? Cool? 5s or 1, 4, 5. Okay, that's good. Always the Arizona judge. No, I'm just kidding.
The error is missing data.
Missing data, that's right. It's all missing data. They're afraid. Believe me, I'm not going to discriminate against you if you don't think a statistic is cool. It's okay. Not a problem with me. We all have. There are some statistics that are pretty stupid, I'll admit. Okay, the covariance, again, we saw this before. Here's the formula to do it by hand for a pair of variables. There's the correlation. We saw all those before, but sure enough, there's a way to do it with matrices. Oh yeah, it's getting better, right? X minus the ones vector times the mean vector gives us X replicated, but if we do X minus its mean replicated, and that thing transposed times 1 over n gives us the covariance matrix. So if I can show you this in R, what am I talking about here? This is X minus its mean. So this is the mean deviation. It's 1, there's X times the 1 vector times X bar transpose. And so that's the mean deviation. If I take the product of the transpose of that with itself, you get this big number. If I divide that by 1 over n, we end up getting with our covariance matrix. So there's our covariance matrix for the data. And you're probably thinking, that's cool. But I don't talk in covariances. Actually, cool? 3, 4, 5. I got a 5, 4, 5. That's good. I'm trying to spice this up. Whatever I could do to make this more interesting, at least for me. I know I'm kind of selfish, but... we can go, though, and switch covariance to correlation like that. If we take the covariance matrix, which I'm calling S here, and multiply it by a matrix D inverse, pre and post multiply it, bless you, whomever that was, pre and post multiplying S by D inverse. What is D inverse? It is the diagonal matrix that is the inverse, where the diagonal contains 1 over the standard deviations of all the variables. So by the way, the inverse of a diagonal matrix is awesome because it's just 1 over the values on the diagonal itself. So D would be this diagonal matrix of standard deviations. Here, I'll just show you. Here is D. D is the diagonal matrix of standard deviations. So right, it's literally the diagonal of S. Diag of diag puts it in a matrix, and the square root of that, because S was a variance, gives us standard deviations. So D is a matrix of standard deviations. The inverse of D is 1 over the value in the diagonal. It's one of the nice matrix inverses you can have. But if you want to get the correlation matrix, you take D inverse times S times D inverse, and sure enough, take a look at what we have here. There it is, the correlation matrix, or if you really want to see core of X, it's the same thing. Cool? Nobody wants to give me, it's like not even ready to, thank you. 5. Yeah, question. I'm waiting for the 1, right? It's like, sorry.
Does the order of operations you're talking about the inverse S?
This will not matter. Well, you need S in the middle there, yes. But apart from that, because D inverse are switchable, then no.
Okay, why does this matter?
Actually, does it matter? That's a good question. I haven't thought about that, and my head is wrapped up. Let's find out. I believe it does. Let me see. Yeah, it does matter. Sorry. I should have known that from just looking at it. It matters because when you do the matrix multiplication, the order of what gets multiplied is set by the order of where the matrices show up. And because that diagonal is 1 over the standard deviation, having it before and after ensures that they all show up dividing by the product of the standard deviations. So it's not a very good explanation. I'm kind of disappointed in myself for not being able to say that immediately, but anyway. So yeah, here's all the numbers. Here's how it works. There's an R. All right, cool. Not so cool. The other thing you could do, though, if you thought that was cool or didn't think that was cool, if you have a correlation matrix and want to get to a covariance matrix, how do you do it? You It's backwards. D, it's no longer D anymore. It's D, R, D, which gives you the covariances, or it should. Those were not the those are the covariances. There they are. Yeah, it's the same value because that is S right there. There you go. So this is one way to switch between covariance to correlation and correlation to covariance. And why I tell that to you is because nearly all of the analysis programs you'll ever use in your life will do something with covariance in it. Am I right, Ahmed? Yeah. But you don't like covariance. You don't speak in covariance. Maybe you do. I don't. Does anyone speak in covariance? Thank you. At least backing me up on that. I don't speak in covariance. It's oftentimes better to speak in correlation. People understand that more. This is an easy way to switch between the two if you really wanted to, if the program won't do it for you. Okay. And in R, you never know. You get what you pay for sometimes. Okay. The other thing we can talk about is the generalized sample variance. We don't usually see that very often, but I'll show it to you here. It's the determinant of the matrix. So this is the generalized sample variance. It's a big number. If that correlation were to be 1, the determinant of the matrix would be 0, and it'd basically say kind of that space spanned by the two vectors would have no volume, right? So what the generalized sample variance is taking into consideration is how long or how much variation there is in each of the vectors, along with what the angle between the two of them happen to be. You don't usually see this very often in statistics. The total sample variance is the sum of the diagonal elements as well. That's the trace right here. That's the trace. Okay. Quickly into multivariate normal. We're going to be into this much more very soon. Before I taught you, before we get into, you saw the math, but just wipe that from the mind. Just not even happen. Didn't even happen. Remember the normal distribution? Was that scary? But you remember the philosophy of it was plug in your data, get a height, right? You plug in the data and the parameters of the distribution, get a height, right? And in the normal for one variable, there's a mean and the variance, or mean and standard deviation, right? For the multivariate normal, it works the same way, but your data now are different. Instead of plugging in one number for your data, it's now multiple numbers. It's multivariate, right? So what does that tell you? Remember, in univariate normal, when we did our example, we talked about sort of the height is a relative frequency for that piece of data compared to the distribution that someone might come from, right? So if you saw two numbers, you could see where they were on the curve. There, let me just draw the curve real quick. That's a bad curve. Anyway, here's one height, here's another one, right? If this is number A and this is B, right here, you'd say that A would be relatively more likely than B under this distribution. The same thing happens for multivariate normal. Now, though, you can't really draw it in one dimension. You sort of have to draw it in two dimensions. So there would be like a bell curve in multiple dimensions here. Is that sort of, can you visualize that a little bit? I don't know if you can see that. I'm not really good at drawing one dimension, two dimensions, let alone three, right? So let's try to describe this. This is the distribution function for it, the normal density itself. So you have a variable that has p observations. This is one person's variable, and you have one person's observation, xp. It's a row vector with capital V variables. What? Yeah, you collected 5 numbers from each person. Cool? And you want to know how likely that is. You plug those 5 numbers in along with the means for all the variables and the covariance matrix right there. And this function tells you the height. The same thing works. It's only now, instead of plugging in one mean, you have to plug in a mean for each of the variables. And instead of one variance, you have to plug in a variance for each of the variables. And then you have to do something with the covariances as well. But the concept still remains, right? Plug in data and parameters, get relative likelihood. Does that make sense? The form of this is much more complicated. So let's look at this here real quick. The mean vector, again, is a column vector of means. The variance-covariance matrix is the square and symmetric matrix of variances and covariances. And you'll note in the model itself, it literally is the covariance matrix that shows up there. And that's why a lot of our multivariate models that use a multivariate normal distribution in the calculation of the likelihood give you numbers with covariances, because that's the numbers that are going into the likelihood function themselves. So this was, at the top here, the univariate normal distribution. And if you squint really hard at it and do some rearranging with algebra, you can make it look like this multivariate normal. In the numerator of the exponent, we have x minus mu squared. Let's break that into x minus mu times x minus mu. In the denominator up there, we have sigma squared, but let's make that sigma to the negative 1/2. Right? Now you can start to see the analog. X minus mu transpose, x minus mu, sigma inverse show up on the top. It's all doing the same type of work. And actually, this term right in here is sometimes called the squared statistical difference. It's telling you how far apart two variables happen to be, or two observations might happen, or an observation is from its mean vector. But it's in standardized units because you've got this sigma inverse in the middle here, which is kind of taking the place of dividing by the standard deviation, the standard of the variance. That squared statistical difference has the most awesome name in the world. It's called the Mahalanobis distance. Ever heard of Mahalanobis before? He's not touring this summer, I can tell you that much. No, that's the coolest name in the world, I think. If I ever have another child, I'm not having the child, but you know what I'm saying. Whomever associated with me is having the child, I've tried to convince them that a name would be Mahalanobis. I don't think that's going to go very well. Although Mahalanobis Hofflin has a great ring, don't you think? I don't know. I'm going to have to tell Lisa. Anyway, I'll report to you after spring break. What's that? You can send it. There you go. That's right. What do you think? Mahalanobis Hofflin? I don't know. This is the determinant of the covariance matrix here. It's kind of like taking the square root. Well, it's raised to 1/2 power. But anyway, there it is. Squared Mahalanobis distance. It's like a z-score in multiple dimensions. But here is a visual depiction of this multivariate normal. It's a bell curve, literally a bell curve in 3 dimensions, right? And on the left-hand side, this might be x1, and this might be x2. And so you've got this shape. The height of that shape tells you the relative frequency for each of those observations that you might plug in. Similarly, if you fly over the top of it and drew a contour map, I know I talked about those previously. I think I've talked about contours in here, right? Did I talk about contours? Yeah. Yeah. Yes.
So that's why there's
mu
the
mu1 and mu2. That's right. Yeah, so there's 2 dependent variables in this case, x1 and x2. Each of them will have a mean, each will have a variance, and there'll be a covariance between them. The mean of x1, and mu x2 is the mean of x2. That's right. Yeah. And then, so if we set the means equal to 0 and the variance covariance matrix to the identity, you'll see that we have 0 covariance, which is like 0 correlation, and our plot is perfectly concentric circles in this density diagram, right? Now take a look at it with the covariance of 0.5. By the way, any covariance matrix with 1s down the diagonal is a correlation matrix. So 0.5 is the correlation. Now, do you see where the likelihood of the data falls? That's sort of, you would expect to see, if you had a correlation of 0.5 between these variables, you'd expect to see most of your data within those circles of the scatter plot there. Kind of interesting, maybe? All right, I'm going to stop there. Actually, I've got 2 more slides and we can stop. The nice thing about multivariate normal is that it's got these awesome properties that you'll never use, that all the programs that you use for it have with it. Linear combinations of multivariate normal are multivariate normal. Subsets are multivariate normal. Anything with a 0 covariance means the variables are independent. and so forth. And we're going to talk about that more on the slides. That sets up our multivariate models because we're going to come back to multivariate normal when we get to our slides, multivariate modeling. So once again, thank you for coming. Somewhere I will send you an email this week when the lectures are up before the next class. And remember, no quiz before the next class. And have a great spring break. And I will hope to see you Tuesday the 27th. Adios.